Okay, in this lecture we're going to start our section 3.3 material on trigonometric substitution. And before we introduce the idea of this method or see some examples of how it works, let me start by introducing when we would use this method. So we would say that integration by trig substitution will be used if the function that we're integrating, our integrand, involves the square root of a sum or a difference of squares and a u substitution fails. So anytime that our integral involves a square root of a sum or difference of two squares and we can't get away with a u substitution, that's when we're going to use this method of trig substitution. And the general idea of this method that we'll see throughout this section is to convert the integral that we're given into a trigonometric integral, so something involving, say, sines and cosines or secants and tangents, which can be evaluated using our previous techniques. Now, for this method of trig substitution, there are a total of 3 different cases that we have to consider. Depending on whether our integrand involves a square root of a sum of squares or a difference of squares, and depending on what order that difference of squares would be given in. So let's consider the first case. So here, case 1 is if our integrand involves an expression of the form square root of a squared minus x squared, where a is just some constant. So if our integrand involves this expression, then we're going to make a change of variables. We're going to let x equal a times sine of theta, so that dx, the differential of x, would be a cosine of theta times d theta. Now, making this change of variables, let's see why we do this. What is this bias? So this square root expression that appeared in our integral, that is the square root of a squared minus x squared, I claim can be reduced to a times cosine of theta. Now let's see how exactly that works here. So if I'm working with the square root of a squared minus x squared, and I choose x as a sine theta, well then x squared is a squared times sine theta squared. So from this expression under the radical, I can factor out an a squared, and I would be left with 1 minus sine squared theta, which would be the square root of a squared, and then 1 minus sine squared is the same as cosine squared of theta. So taking the square root of this, I'm left with just a cosine theta. So our goal is to take these expressions involving, say, the square root of a difference of squares and make some substitution of my variable x by something involving a trig function, in this first case, something of the form a sine theta, so that that radical expression, the square root of a squared minus x squared, reduces to a times cosine of theta. So let's look at an example to illustrate how this works in a little more detail. In our first problem, we're asked to evaluate the integral of the square root of 25 minus x squared all over x dx. So when I see this, as soon as I see this numerator involves the square root of 25 minus x squared, that is the square root of a difference of squares, I immediately think about using a trig substitution. Now, I could try using a u substitution here, since my integrand involves a composite function, but we'll find that if we were to try a u substitution, we get stuck with these extra factors of x that can't be canceled out nicely. So if this substitution initially fails, let's move to our trig substitution. And our numerator is of the form square root of 25, or 5 squared, minus x squared. So in this case, we're going to make the substitution x is equal to a. So in this case, the constant that was being squared was 5 times sine of theta. And now I want to rewrite this integral in terms of theta. So I have what x is. Now I still need to find the differential dx. I need to rewrite it in terms of d theta. So if x was 5 sine theta, then dx would be 5 cosine theta d theta. And this square root of 25 minus x squared reduces to 5 cosine theta. So by making this substitution, let's rewrite our integral. We had the integral of the square root of 25 minus x squared all over x dx. So in terms of theta, our numerator is 5 cosine theta. We were dividing by x, which was 5 sine theta. And then on the end, we had dx, which we found was 5 cosine of theta d theta. So let's simplify a little bit here. We see we could cancel one factor of 5 in the numerator and denominator, and I would be left with a constant of 5, which I can bring out in front of the integral. And then I have a cosine of theta times cosine of theta, or cosine squared theta, divided by our sine theta d theta. So by making this trig substitution, I've now reduced this to a trig integral. And in order to evaluate this, I can make use of the fact that my numerator, which is cosine of theta squared, is the same as 1 minus sine of theta squared. And the whole thing is still being divided by sine theta. So if I split this integral into, or this integrand into two parts, I would have 1 over sine of theta, which is cosecant theta, minus sine squared theta over sine theta, which is sine theta d theta. And now we know how to evaluate these, the antiderivative of these trig functions. So let's see what we have. We had our constant 5 out in front, and the antiderivative of cosecant theta is the negative natural log of absolute value cosecant theta plus cotangent theta. Recall we had derived that formula in our section 1.5 on substitution. It worked very similar to the antiderivative for secant theta. And then minus the antiderivative of sine theta, which is negative cosine theta. So we get a plus cosine theta. And once I found my antiderivative, I can include the plus c, my arbitrary constant, to get the most general antiderivative. Now what we have here is an answer in terms of the variable theta. But I don't want an expression in terms of theta for my final answer. I want something in terms of the variable x, the same variable that we started with. So let's see how we could go about converting from theta values back to x values. So in order to do this, I'm going to make use of a reference triangle here. So let me maybe use a different color. So I want to consider a right triangle, which I'm going to refer to as a reference triangle, that would be formed by this angle measure theta. Now in my substitution, I had x was equal to 5 sine of theta, or equivalently, sine of theta is x divided by 5. Now when we think about how sine of theta would be defined in terms of the sides of a triangle, it would be given by the opposite, or the ratio of the opposite over the hypotenuse lengths of this triangle. So the edge opposite of theta would be x, and my hypotenuse would be 5, since we said sine of theta was x over 5. And sine of theta is defined as the opposite over the adjacent sides. So I still need to find the third edge of this triangle, which I can do by using the Pythagorean theorem. So solving for the length along this third edge, it would be given by the square root of 25 minus x squared. And this reference triangle will allow me to determine the values of all of these trig functions, say cosecant theta, cotangent theta, or cosine of theta, in terms of x. So let's look at it. We have, if we distribute our constant 5, a negative 5 times the natural log of the absolute value of cosecant theta. Now cosecant theta is 1 over sine of theta, so we would have the ratio of the hypotenuse over the opposite edge. In other words, 5 over x, or the inverse of our sine theta function. Plus cotangent of theta, or 1 over tangent of theta, which would be the ratio of the adjacent over the opposite edges. So from our reference triangle, the edge adjacent to theta was the square root of 25 minus x squared, divided by the opposite edge, which was x. And then plus cosine of theta, which is given by the adjacent over the hypotenuse edges, so 25 minus x squared over 5 by using our reference triangle, plus our constant c. So let's see, for the sake of simplicity, that constant negative 5, let me keep out in front for right now. And then distributing this constant of negative 5, I have negative 5 times the natural log of the absolute value of 5 plus the square root of 25 minus x squared all over x minus, plus, this negative was not out in front here, but rather in front of just the logarithmic term. So then we have our negative 5 natural log of 5 plus square root of 25 minus x squared over x, plus 5 times this second term leaves us with the square root of 25 minus x squared plus c. So this would be our antiderivative of that function. So we see how this method of trig substitution works in this first example. Now let's consider some of our other cases. The second case of a trig substitution would be the case where our integrand involves an expression of the form square root of x squared minus a squared. So in this case, we could make the substitution that x is equal to a times secant theta, so that the differential dx would be a times secant theta tangent theta d theta. And making this trig substitution allows us to rewrite this square root of x squared minus a squared as a tangent theta. To see how that works, we could look at the square root of x squared minus a squared. Now, if x is equal to a secant theta, x squared would be a squared secant squared theta, and then we are subtracting a squared. So from under the radical, I can factor out an a squared, and I'm left with secant squared theta minus 1, which is equal to tangent squared theta. So taking the square root of this expression, I'm left with a tangent theta. So if our integrand involves a square root of a difference of squares where we have x squared and then we're subtracting a squared, we would use this trig substitution. So as an example, let's consider something similar to our first problem. We're asked to evaluate the integral of the square root of x squared minus 16 all over x dx. So whenever I see this expression in my numerator, which involves the square root of a difference of squares, that should immediately make me think of using a trig substitution. And for that form of integrand, we're supposed to make the substitution x is equal to a, which in this case would be 4, since we had x squared minus 16, or 4 squared, times secant theta. So then dx is 4 secant theta tangent theta d theta, and our radical, square root of x squared minus 16, is equal to 4 times tangent theta. So rewriting our integral in terms of theta, let's see what we have. So our numerator we found was given by 4 tangent theta divided by x, which was 4 secant theta. And then we had a dx on the end, which was 4 secant theta tangent theta d theta. So we see a few terms will cancel here. We can cancel a factor of 4 in the numerator and denominator, as well as one factor of secant theta. And so we're left with 4, which I can bring out in front of the integral, times tangent squared theta d theta. So thinking back to our method for trig integrals, well, to evaluate a trig integral involving an even power of tangent, we could make use of the trig identity that tangent squared theta is equal to secant squared theta minus 1. And we know how to find the antiderivative of these functions. The antiderivative of secant squared theta is tangent theta minus the antiderivative of 1 with respect to theta would be 1 theta, and we can add our constant of integration at this point. So now we need to find our answer in terms of x. So let's see what we have here. We had, maybe if I first distribute my 4, a 4 tangent theta minus 4 theta plus c. So this is 4 times, let's see if we can find tangent theta. So there's a few ways we could do it. We could make use of this reference triangle approach that we used in the first example. Or if I look back at my previous work when I was doing the substitution, I have an expression involving tangent theta right here. So if I solve this equation for tangent theta, I have the square root of x squared minus 16 over 4. And then we had minus 4 times theta. So let's think about how to find theta. Now, using our substitution, we had x was equal to 4 secant theta. So a little scratch work to the side here. If x is 4 secant theta, that means that x over 4 is equal to secant theta. And so solving for theta, we would have the inverse secant of x over 4. So we've got a negative 4 times the inverse secant of x over 4 plus our constant c. Or simplifying this first expression a little bit, I can see this factor of 4 will cancel, and I'm left with the square root of x squared minus 16 minus 4 times the inverse secant of x over 4 plus c. All right. So let's look at our third case. The third case of a trig substitution arises when our integrand involves something of the form square root of x squared plus a squared. That is a square root of a sum of two terms squared. So in this case, we would make the substitution x is equal to a tangent theta, so that the differential dx is given by a secant squared theta d theta. And in this case, our expression involving the square root of a squared plus x squared will reduce to a secant theta. To see why that's the case, let's look at this expression. For the square root of x squared plus a squared, if x is equal to a tangent theta, then x squared is a squared times tangent squared theta, and then I was adding an a squared. So if I factor out an a squared from the expression under the radical, I'm left with tangent squared theta plus 1, which is secant squared theta. So taking the square root of this expression, we have a secant theta. So let's look at an example of this. Here we are asked to evaluate the integral of dx over x squared times the square root of x squared plus 4. So as soon as I see that my integrand involves this square root of a sum of squares, x squared plus 4, or 2 squared, I should immediately think of a trig substitution. Now again, for all of these are involving composite functions, so we could try a u substitution from the beginning, but we'll find pretty quickly if we try a u substitution initially that it will not work. So if we instead make this trig substitution, we would take x to be 2 times tangent theta, in which case dx is 2 secant squared theta d theta, and the square root of x squared plus 4 is 2 secant theta. So rewriting our integral in terms of theta, we have the integral of our numerator was dx, which was 2 secant squared theta d theta, divided by x squared. So squaring x, we would have 4 tangent squared theta times the square root of x squared plus 4, which we found to be 2 secant theta. So let's simplify a little bit here. We see that we can cancel a factor of 2 on top and bottom, along with 1 power of secant theta. So we then have a constant 1/4, which we can bring out in front of our integral. And I'm left with secant theta divided by tangent squared theta d theta. So this integrand, after simplifying, is a little bit messy. It involves secant theta and 1 over tangent squared theta. And we're not very familiar or not as comfortable working with the trig functions secant and tangent. So for some of these problems, it's often helpful to rewrite the trig functions that we're left with in terms of sines and cosines, because we're a little more familiar with working with the sine and cosine trig functions. So let's take a look at this. We had a constant of 1/4 out in front. Now secant theta is the same as 1 over cosine theta. And then we were dividing by tangent squared theta. Now, tangent theta is given by sine over cosine, but if we're dividing by tangent, that would be the same as cosine over sine of theta. And that quantity was being squared. So now we have a 1/4 times the integral of, well, we've got a 1 over cosine theta times a cosine squared theta over sine squared theta, d theta. And this allows us to cancel 1 factor of cosine theta from the numerator and denominator, and we are left with 1/4 the integral of cosine of theta over sine squared theta d theta. So we now have a trigonometric integral involving powers of sine and cosine theta. We see here that we have an odd power of cosine theta, just cosine theta to the first, and everything else is written in terms of sine theta. So using our method of trig integrals, we could make a substitution where u is taken as sine of theta, so that du would be cosine of theta d theta. And rewriting our integral in terms of u, we have a 1/4, and our numerator was cosine of theta d theta, which is simply du, divided by sine squared of theta, which would be u squared. So for our antiderivative, we have a 1/4 times negative 1 over u to the first power plus c, or negative 1 over 4 u, which was sine of theta, plus c. Or if we prefer, we could rewrite this as a negative 1/4. The 1 over sine theta is the same as cosecant theta, and then plus c. So whichever way we prefer to write this. Now in our final step, we need to move back to an answer in terms of x. So my answer at the end here either involved a sine theta or cosecant theta, depending on how I wrote it. And I see that from my earlier work, well, none of these expressions involve either sine of theta or cosecant theta. So here I'm going to need to make use of a reference triangle. So let's consider the right triangle produced by this angle measure theta. Now, since in our substitution we said x is equal to 2 tangent theta, that means tangent theta is equal to x over 2. And tangent, in terms of the sides of a triangle, is defined as the ratio of the opposite over the adjacent sides. So since tangent theta was x over 2, the opposite edge is x, the adjacent edge is 2. In solving for the hypotenuse using the Pythagorean theorem, we have the square root of x squared plus 4. So going back to our answer here, we have a negative 1/4 times cosecant theta. Now cosecant theta, or 1 over sine of theta, would be given by the ratio of the hypotenuse, which was the square root of x squared plus 4, over the opposite edges, which was x, plus c. So we have the following expression, or if we care to simplify this just a bit further, we would have the negative square root of x squared plus 4 divided by 4x plus c. So in this lecture, we've considered when we would use the method of trigonometric substitution, which again is any time our integrand involves the square root of a sum or difference of squares and a substitution fails.